record on this computer. Okay. So I'm going to review something that I did yesterday and maybe started on Tuesday, which is eigenfunctions and eigenvalues of self-adjoint systems. And I want to go through this because it's so related to stuff in quantum mechanics, and quantum mechanics is is so important. So you've got a regular Sturm-Liouville system, and it's a set of regular and self-adjoint differential systems. That's section 31. They have the same differential operator interval, boundary conditions, and domain, and whose differential equations are all of a Sturm-Liouville type. And the equations differ by the eigenvalue, and the functions p, q, and rho are real and continuous. P and rho are positive on the interval. And the weight function can vanish at a couple of points, but it's got to be basically positive. Since the differential systems are self-adjoint, the real or complex functions in the domain are twice differentiable in the interval and satisfy two homogeneous boundary conditions that make the boundary terms vanish. And then what you have is that the real differential operator obeys this equation, has this symmetry, which we described as, which we said was meant that it was self-adjoint or Hermitian, or self-adjoint or Hermitian. So suppose psi I and psi j, I'm writing this in sort of quantum mechanics notation, are eigenfunctions of this real differential operator L with eigenvalues lambda I and lambda j. So we have these two eigenvalue equations. And so we multiply this one by psi j star, we multiply this one by psi I, we take the complex conjugate and multiply of this one, multiply by psi I, we integrate the two of them and use the hermiticity in this form that this is equal to that. Then what we get is that this minus that is 0. And consequently, lambda I minus lambda j star times this vanishes. And what we're using here is this hermiticity property up here. Maybe I should make that more explicit, because as I just read through it, it wasn't obvious to me what I was doing, to tell you the truth. So the idea here is we have this thing here, and the point is that this is the same as this one. So in other words, what we can do is we can move the L forward, basically. That's what actually happens here. You take the L here and you can move it forward to here, and you have the same thing. Well, if you move the L forward here past the psi and the parenthesis and the star, you just have two things that exactly cancel. That's why it's 0. And on the other hand, using the eigenvalue equations, we get that's lambda I minus lambda j star. And so we said I equal to j, and we get this equation. And now this thing is obviously positive because the wave function's not 0, or the eigenfunction's not 0, and rho might vanish at 1 or 2 points, but it's not identically 0. And so that means we can divide by this, and then we get that lambda I star is equal to lambda I. So that means the eigenvalues are real. So all the eigenvalues of a regular I'm just going to say SL system are real. And now if they're real, we go back to this equation and we set, we realize that lambda j is real. So this is just lambda I minus lambda j times this equals 0. So that means then that if the eigenvalues are different, we divide by the difference in the eigenvalues and we get that the eigenfunctions are orthogonal. So eigenfunctions corresponding to different eigenvalues then are orthogonal. And now the differential operator is real, the eigenvalues are real, the weight function is real. So we can write, if we have this eigenvalue equation, the complex conjugate gives us that. So that tells us that that both psi and its complex conjugate solve this equation with the same eigenvalues. And then that means that the real part of psi satisfies them, but so does the imaginary part. And so we have effectively two real eigenfunctions with the same real eigenvalue. On the other hand, the eigenfunctions satisfy boundary conditions, and the boundary conditions eliminate the extra function. And so what you have then in a regular SL system is there's no degeneracy, and all the eigenvalues are orthogonal and can be normalized on the interval with a weight function like this. Now, when I say there's no degeneracy, what I mean is you don't get this cheap degeneracy that's universal because of the real and the imaginary part being solutions. It may be there's an additional symmetry in the problem so that you have two eigenfunctions. I'll have to think about that. Now, what is true is that we saw that if you have a second order differential equation, you can use Wronski's formula to take the one solution, y1, and get a second solution, y2. And on the other hand, the second solutions don't obey the boundary conditions of the domain typically. And for example, the Bessel functions are orthogonal. Not orthogonal. The Bessel functions of the second kind, for example, are infinite at the origin and so forth. Or for example, suppose we consider the infinite square well potential, then the solutions in here can be cosine or sine, but only sines satisfy the two boundary conditions. So that's a very good example, by the way, that you should study carefully, the example of the infinite square well. It's something you've probably seen in a quantum mechanics course, but it's very instructive, has all these features. Now, what we want to see here, this is an important fact here. A set of eigenfunctions of an SL system is complete in the mean in the domain of the system if every function in the domain can be represented by a series that converges in the mean. So this is a series of the eigenfunctions, and we want to say this can approximate in the sense that that it converges in the mean. Oh, sorry about that. That is to say that the integral of the absolute value squared of the error being the difference between the function and the partial sum of the first n eigenfunctions with appropriate coefficients, multiplied by the weight function, integrated over the interval, limit as n goes to infinity, 0. Okay, so that's convergence in the, I don't know why the hell this mouse has to be so goddamn responsive. So that's basically a definition of convergence in the mean, and I'm going to show or at least the proof is described in the book. I don't know if we're going to go through every step today, but if you have a Sturm-Liouville system, a set of eigenfunctions is complete in the mean if this is true. Complete in the mean in the domain, and that's every function in the domain. So the domain here, for example, in the case of the infinite square well, it was a set of all functions that vanished. Let's use a different color for the moment, that vanished here and were twice differential and satisfied the differential equation. No, actually, all we're saying is that the domain is just twice differentiable and satisfy the boundary condition. We don't ask them to be solutions of the equation. So suppose we have, well, first of all, this is the formula for the coefficient. And the reason for that is that we have orthonormality of the eigenfunctions. And so since the eigenfunctions are orthogonal, if we're saying that f of x is this sum of, say, ai ui of x, then the integral f of x rho of x uk of x dx over the interval is going to be a sum ai and then an integral ui of x rho of x uk of x dx, and this is going to be a sum ai delta ik, which gives us ak. So that's where this formula comes from, namely that this is equal to a sub k. Now, if we put that formula into the series, by the way, a series of this form, you see, it's a generalization of the Fourier series. And so people now call these things, these generalized series, Fourier series. I don't know if Fourier actually realized how general his work was, but he may have, I don't know. Anyway, if we write ai as this integral, from a to b of f of y dy, ui of y times rho of y, and the rest of so let's see, this is a little bit confusing now that I look at it. We're saying that ai is this ai ui. So there's ui, and then the ai has the f, and looks like that, where this is the ui of x is that one, and everything else, this, that, and that is just creating the coefficient ai. So now we have this expression here, and maybe I should build that up again. So what we have is, we're saying that f of x is a sum ai ui of x. So that's going to be a sum ui of x. And now what is ai? Well, ai, using this formula, ai is an integral a to b f of y, I'm changing variables to y, ui of y dy. And so now this thing is the following. It's f of y integrated ab, and everything else is a sum ui of x, ui of y, rho of y, y here, dy. And that, in fact, is what we have here. At least I hope it is. And so what do we have here? We have here f of x is an integral a to b of f of y times parentheses dy. So this thing has to be delta of x minus y, because when you integrate f of y times the parenthesis, you get f of x. And so that gives us the really important formula, namely that the sum over I from 1 now to infinity of ui of x, ui of y, rho of y is the delta function. And of course, this sum is non-zero only when x equals y. And so we could equally well write this as a sum rho of x, ui of x, ui of y, or any combination of them. And in other words, the orthonormal eigenfunctions of every SL system on an interval are complete in the mean in the domain of the system. Well, I'm just making that as a statement. The completeness follows, and we'll get to that in a moment. The completeness follows from the fact that the eigenvalues of an SL system, a regular SL system, are unbounded. And when arranged in increasing order, they go to infinity with the index. And that's what gives us the completeness. And for example, in the case of the square well, so let me pop over to square well. The eigenfunctions look like this. The eigenvalues look like that. And n, as n goes to infinity, the eigenvalues go to infinity as n squared. So that's how it is that that's an example of these functions. The sine functions we know are complete. At least they're complete for functions that satisfy the boundary conditions, namely that they vanish at the endpoints a and b. So for any function that's real and continuous and that vanishes at a and b, you can write it as a sum of sine functions like this. And then the eigenvalues of the differential operator. And the differential operator here is minus h bar squared over 2m u double prime, second derivative, because this gives you the momentum, plus the potential times the wave function is equal to the energy times the wave function. And now the potential here is some constant v between a and b, and then infinite outside of a and b. So that's the I think now I've gotten us back to where we were. Yes, okay. So the unboundedness of the eigenvalues, well, it's pretty obvious if this is the expression that the eigenvalues are going to be unbounded, because you can make E arbitrarily big. E of u is sort of the energy of the function u. You just, without making n of u, the norm of the function u, big, what you do is you just make u wiggle a great deal. So in other words, here's an example where the function u just is sine of x, and it goes from zero to zero as x goes from 0 to pi. But I've added to it 0.1 times sine omega x, where omega is 200. And so then you get something with a huge amount of wiggle. And so the energy given by this expression is going to be quite high. And so you can make the eigenvalues arbitrarily high. And what people normally do is they say, well, you see, this turns out, the eigenvalue turns out to be E over N. And that's because if you integrate this by parts and use the boundary conditions, then what you find is lambda. I hope I've done that, or if not, I'll be doing that shortly. So Coulomb and Hilbert give a proof that here, let's see. Coulomb and Hilbert consider this general SL system, and what they show is basically, I'm going to skip the details of the statement here, but what they show is that the eigenvalues go to infinity basically as n squared. So it's like the square well. Now, what about the completeness of the eigenfunctions? Well, the completeness of the eigenfunctions follows from the fact that the eigenvalues diverge. Another example of this is the Fourier transform. That is to say, we can write any function f of x as an integral e to the I kx some f tilde of k dk. And what are these? These things are the eigenfunctions, and they're eigenfunctions of minus d2 dx squared on e to the I kx is equal to k squared e to the I kx. So they're eigenfunctions with this eigenvalue, and these eigenfunctions then, as you know, from the chapter on Fourier transforms, they can express basically any square integrable function in this way. And why is that? Well, it's because we can integrate here from minus infinity to plus infinity. So the eigenvalues k in absolute value go to infinity as you, well, it's continuous, so they're not labeled by an index n. It's just that the eigenvalues are unbounded. Now, the proof of this, I'm happy to go through the proof in detail if one or two students want to see the proof in detail. If, on the other hand, nobody does, then I can just say, well, read it at your leisure and skip and go to the next topic. But so can we have, can people use some sort of either say that you want, in other words, what, I don't know, in the chat, in other words, the easiest way maybe is to, in the chat, say skip or do. And if various people would use the chat function to say skip or do, okay, I've got one person for do, another person do. All right, we got 3 do's. I think all right, 4 do's. All right, so this is okay. All right, so what are we going to do to work this out? Well, the first thing is to define some inner products. And of course, this, remember, way back in the case of, way back in chapter 1, I emphasized inner products, and that they were important because they lie at the basis of many, many concepts. And here are inner products that are quite amusing. Inner products of two functions, and we have here two different inner products. And if we integrate the first one by parts, then we see this turns into FLG plus the boundary terms, but this vanishes, so E is just FLG. So that's the first topic. Next, we can use the first n orthonormal eigenfunctions of the system. So LUK is lambda k, rho UK, and we approximate an arbitrary function in the domain as a linear combination of the eigenfunctions with coefficients. And the coefficients, as we saw before, they're given by the n inner product of f with uk, that is to say rho f uk integrated dx. So now we want to see that this series converges. And what we do first is say, well, what's the error? The error is the difference between the function, the arbitrary function that satisfies the boundary conditions, and this linear combination of eigenfunctions. And the first thing to notice is that this is a very cute little thing, namely that this error is orthogonal to the first n eigenfunctions, because if you take, for example, n of Rn UK, well, this is going to be essentially, let's see, what did I write here? This is going to be effectively n of f UK minus the sum ck. Oh, hell, I did a k. All right, hold on. Let me change. Here's what I'm going to do. I'm going to make this a different index. So I'm going to call this I, say. And then this is a sum ck n of uk ui. Well, uk ui is delta, is a Kronecker delta because they're orthogonal. And on the other hand, n of f and uk is ck, so n of f and ui is ci. So the first term here, first term is just ci. On the other hand, these guys are orthogonal, so this is delta ki, and so we have ci minus some ck delta ki, and so that is just ci minus ci, which of course is 0. So that tells us that the remainder, or the error, is orthogonal to the first n eigenfunctions. And the next eigenfunction is one that is the function that satisfies the boundary conditions and minimizes this ratio. It minimizes it in the space of all functions that are orthogonal to the first n eigenfunctions. And so R of un plus 1 is lambda n plus 1. And consequently, what we have here is that lambda n plus 1 is is R. Now I've lost track of what I was saying here. So let's Right. This is the minimum value of the ratio. So it's, in particular, it's, since we've seen that Rn is orthogonal to the first n eigenfunctions, that's what we went through laboriously here. So consequently, the next eigenvalue is less than or equal to this ratio for Rn. And consequently, n, which is the norm of Rn, is less than or equal to E over the lambda. And now, since this goes to infinity, Rn goes to 0. Now, so we're done if we can show that this thing is bounded, that the energy of the error goes to 0, or at least is bounded. We don't even need to show that it goes to 0. So what is the energy of the remainder? Well, it's the inner product, it's the E inner product of F minus the sum. And now if you multiply all those out, you get all of this. And let's see. E of FUK, which occurs here, is lambda K CK. E of UK UL is this, which is that, which is effectively the Kronecker delta. So if you use these two formulas in here, what you get is that E of Rn is E of FF minus something. And in as much as the lambdas are going to infinity and the CK squareds are positive, it's pretty clear that this thing here is bounded, because eventually this becomes negative. And consequently then this is bounded. E of Rn is E of R, effectively the E inner product of Rn with Rn is less than the E inner product of F with F. And so that's this equation. And so now we can say, well, we had Rn as the numerator here. We can now say that this is less than that. These guys go to infinity. Now, what I can see as I went through this is there's something that was a little bit skipped over, but I hope I did this on Tuesday, namely that we have this ratio, and the ratio of the E norm to the N norm is the minimum of that. The absolute minimum of that is the lowest eigenvalue, and then the minimum of that over functions that are orthogonal to the lowest eigenfunction gives you the second eigenvalue, and so forth. That was something that, let me see if I can find it here. Right, and oh, I've gotten this thing hung up looking for this. Sorry, I'm just, oh, here we are. Yes, whoops. Previous. Oh, Jesus. Let me see. I'm having a lot of trouble here finding this thing, and the way to find it, I think, is to go back to a certain place, to an earlier part of the book, and then to search for the word yes. That doesn't occur that often. And oh, sorry to take so long to do this. Okay. In other words, that was here in a constrained variational problem. So in other words, here I was talking about E of U and N of U and the ratio being R of U. And the deal is that the minimum of the ratio is the least eigenvalue. And so that, let me just say what section that was. It's section 35, a constrained variational problem. So it's the section right before the where I started class today. So there are a lot of details. I think they're all done in the book carefully. So basically, one can expand arbitrary functions in terms of these SL Eigen functions. And now, the arguments really did not involve in detail whether the interval was finite and whether P was positive and so forth. And so the completeness of the eigenfunctions of an SL system are much more general than what is proven in my book. What they can do is they can, these eigenfunctions can give us a formula for Dirac's delta function. And the formula involves the weight function, but when I worked it out a moment ago, you know, I was talking about the thing in parentheses, I had it as, I think, rho of y, but it could be rho of x, it could be rho of y, or it could be, you know, rho of x to the 1/2 power and rho of y to the 1/2 power. It doesn't matter, just rho of x to the alpha and rho of y to the 1 minus alpha times the sum of the eigenfunctions gives you the delta function. And so that's how the, this is a statement of the completeness, because you see, if this delta function relation holds, then what we can say is that f of x is equal to the integral of delta of x minus y, f of y dy. But on the other hand, that delta function, let me just write it as rho of, I'll just write it as rho of y. Sum ui of x, ui of y, f of y dy. I think I've got that right. Okay. So what does this tell us? Well, these integrals rho of y, u of y, f of y dy is something that depends only on I. And so this is a sum ci ui of x, where ci is equal to integral rho of y, ui of y, f of y dy. So in other words, if we define these coefficients to be these integrals, then we have then the delta function tells us that delta function representation tells us we can expand f of x as a sum of the eigenfunctions. And the delta function relation then guarantees the completeness of the eigenfunctions, and it gives us formulas for the coefficients. And as an example of that, I did a MATLAB plot of the first 10,000 terms of a Bessel representation. So here I use Bessel functions, and the eigenfunctions that are normalized were UK n was this ratio. These are just normalization constant. The basic thing is Jn of Znkx. And what I'm doing then is a sum over k for each n. So n says, what is the differential equation? This is the nth Bessel equation. That's the n. And that nth Bessel equation has an infinite number of eigenfunctions, the eigenvalues being Znk squared. And they're actually zeros of a Bessel function. But anyway, the analog, the Dirac's delta function for this then is the product of the eigenfunction of x, eigenfunction of y, summed over them all, multiplied by the product of weight functions. And what I was illustrating here, by letting alpha vary, so I had alpha equal to 0, alpha equal to 1/2, and alpha equal to 1. And in each case, I changed y so that the delta functions didn't all pile up on the same point. So I have, this is delta of x minus 0.47. This is x minus delta of x minus 0.5. This is delta of x minus 0.53. And what you see is that the sum gives you a very good representation of the delta function. But of course, it's only the first 10,000 terms. You're supposed to sum to infinity. And then what happens is that these oscillations become tighter and tighter and smaller, and this peak goes higher and higher, and it converges to something that's really a delta function. There are some inequalities. This is something much simpler than what we've just struggled through, namely that obviously this thing is non-negative, and if you now use this formula, which I can flash for you if I, well, that's strange. Anyway, oh Christ, now where am I? All right, inequalities of Bessel and Schwarz. All right. So what it follows from this that the integral of the norm squared of f weighted by rho is greater than or equal to the sum of the coefficients, and then you can use you can then derive also this Schwartz inequality that the norm squared of f times the norm squared of g is greater than or equal to the absolute value squared of this inner product. Now, so I'm going to shift gears just a little bit here to Green's functions. And of course, we talked about Green's functions before, but here I want to just remind you that a Green's function is something that's the Green's function for a particular differential operator. So if L is a differential operator, then G is the Green's function for that operator. And in fact, to emphasize that, I probably should have called this G sub L. So let me do that. I hope I did that correctly, in which this, So in other words, to make it clearer, I would say I'd put a capital L subscript there. In other words, G sub L is the Green's function for the differential operator L. And the idea is that L on G sub L of X is delta of X. Now I have a little n here. That depends, that's the number of variables in X. In other words, X might be a single value, single variable, just a real number. Then n is 1. X might be a 2 vector like XY, then n is 2. If it's point in 3 space, n is 3. So that's the idea there. An example of that is Poisson's Green's function, and that is minus Laplacian. So the differential operator is minus the divergence of the gradient on G, and that has to give you a 3-dimensional delta function. And the answer then is that G, you can find the answer by writing the Green's function as a Fourier transform, and then writing the delta function as a 3-dimensional Fourier transform. And then you apply the Laplacian or the divergence of the gradient to G, and the derivatives pull down a k squared, well, a minus k squared, but there's that they absorb that minus, the i's absorb the minus sign, and you want that to be the delta function. So the integrals look the same, except here it's k squared g, and there it's just 1. So clearly little g is 1 over k squared, and so we write it this way. So this is the Green's function for that. And this is the most important, probably, Green's function in physics, 1 over 4 pi r. And this is the Coulomb potential. It's also the gravitational potential. So it's just occurs everywhere. Helmholtz has a different Green's function equation, and it's minus Laplacian minus m squared. V is rho, and to solve this kind of equation, well, you want a Helmholtz Green's function, and it turns out that the Green that you can show that GH is this, and there's another there's a modified Helmholtz equation where you change the sign of m squared. And for that, you get the Green's function is actually the Coulomb potential. And you remember that the Green's function, the Coulomb Green's function, 1 over 4 pi r, it turns out it has this lovely expansion in terms of spherical harmonics, which we'll get to in a couple of weeks. Spherical harmonics and ratio of r lesser to the L power divided by r greater to the L plus 1. And here r, theta, and phi are the coordinates in spherical coordinates for the point x, and theta prime, phi prime, and the other r are the spherical coordinates for x prime, and r lesser is the smaller of r and r prime. And consequently, the potential due to a charge distribution is given by the integral of this Green's function times the potential. And that is this expression here. And these things are called multipoles. And you can pull out the theta part, and you integrate over theta phi and r prime, and you pull out, you integrate over theta prime, phi prime, and r prime, and you pull out the theta phi and r. And if r lesser is r prime and r greater is r prime is r, then we can write the thing this way. And so you're integrating over everything and the multipoles are these things here, QLM. And so the multipole expansion of the potential then looks like this. This is when your point of observation is outside the region of charge. So R is greater than R prime. If one has enough symmetry, well, even if one doesn't have enough symmetry, one can always express this sum in terms of a Legendre polynomial, and that's one of the topics we'll get to shortly. And that allows you to write the Green's function more simply, namely that it's a ratio of R lesser over R greater to suitable powers times the Elf Legendre polynomial of the dot product of the vectors. There's also Feynman's propagator, an example of a Green's function, and it's a Green's function for m squared minus box. And let me say what box is. Box here is triangle minus d0 squared. And so this is the divergence of the gradient minus the second derivative squared. D0 is just the time derivative. So this is the divergence of the gradient minus d by dt squared. Let's see, this is maybe I'll just try to fix this a little bit. Okay, so that's what box is. And so we want m squared minus box on the Feynman's Green's function to be the four-dimensional delta function. And you can see that that works here. And so maybe it's worthwhile just looking at that. Why is it that this works? Well, if we have m squared minus box acting on delta f of x, well, this is going to be, as I say, integral d4th q 2 pi to the 4th. And then we have e to the I qx. And what do we have in the numerator? Well, m squared. And then we have the gradients, the spatial gradients. So that brings down minus k squared. The temporal gradients with, oh, I screwed up. Hold on. And we're dividing by here. Oh, I said K when I meant Q. Nuts. All right, hold on. Okay, and then in the denominator, what we have is, of course, m squared and plus q squared. Let me show you what q squared is. It's q vector squared minus q0 squared. And then Feynman snuck in a minus I epsilon. Well, basically the numerator cancels the denominator. And so this is an integral d4th q over 2 pi to the 4th e to the I qx, and that's delta 4th of x. So that's in other words, the four-dimensional delta function, which is to say it's delta of x0, delta of x1, delta of x2, delta of x3. Okay. So what actually is this? Well, to figure this out, what we do is we have to, of course, rewrite this in terms of things that are a little bit simpler. And what you can do, as I think we saw, or at least if you read chapter 6 in its entirety, you learned that you could write delta f as delta plus times a step function of the time times I plus I times a step function of the minus time and a delta plus of x and minus the time. And now it turns out that this delta plus is a function that is Lorentz invariant. That is to say, if you make a Lorentz transformation on the 4-vector x, x0, x, you don't change the value of delta plus. But what makes a lot of difference is whether this x is space-like or time-like. In other words, whether the x is bigger than the x0 or not. In other words, whether the length of this 3-vector is bigger than the time. If it is, we say it's space-like, and then this is a convergent integral. And in fact, you can write it this way. On the other hand, if the 4-vector x is time-like, this is an extremely singular function. It's something like it's somehow related. Its real part can be related to a derivative of a delta function, but it's quite a singular thing. Anyway, let's go back to the relationship between eigenfunctions and Green's functions. And well, here's a Green's function based on the expansion of the delta function in terms of eigenfunctions of this differential operator with these eigenvalues. Right. Of course, when I say these eigenvalues, the m squared is just playing a cipher role here because I'm just adding m squared times the exponential twice. But in other words, let's see, let's switch to blue. What's being said here is that e to the plus or minus I k y minus d by dy squared plus m squared is equal to k squared plus m squared e to the plus or minus I k y. So these things here are eigenfunctions of this differential operator with these eigenvalues. And so we see we can write the delta function in terms of the eigenfunctions. And one way of going in that direction, although we've sort of been there several times, is to say, well, if LUN is lambda n rho UN, and we've got that the U's are orthogonal when properly weighted, well, one way to do that is to say the Green's function is just the outer product, the product of the eigenfunctions divided by the eigenvalues summed, because then when you have L on G of XY, X minus Y, let us say, you get L on UK, that cancels the lambda K, you then have all of this, and that gives us the delta function. And so that shows you that one way of writing, this is just sort of repeating that this is a way of writing Green's functions. This section here, I'm going to skip it. If you guys want to read it, feel free to read it. I think it was just a little too much trouble. Let's go to the principle of stationary action, because this is really important in electrodynamics, general relativity, quantum field theory, and so forth. The idea is we have a scalar field. L is its action density or its Lagrangian. S is the action. The action's an integral over all space and all time of this action density, and that gives us the action. Now, the principle of least or stationary action says that the field phi that satisfies the classical equation of motion is the one for which the first order change in the action due to any tiny variation of the field vanishes. So delta S is 0. And as usual, I'm going to assume that the action density just depends upon the field and its first derivatives. So then the change in the action is the integral of the change in the action density, and that's partial L partial phi d phi plus the chain partial of L with respect to the derivatives times the change in the derivatives. The change in the derivative is the derivative of the change, and so we wind up with the change in the action is given by the integral of this. But on the other hand, we can integrate by parts, of course, and the surface term vanishes because we're saying that delta phi is non-zero only at some finite point, not at some surface at infinity. And so when we have the integral of delta phi times the square brackets vanishes. On the other hand, Lagrange's what this then says is that the field satisfies the classical equation of motion, which is that the eighth derivative of this partial is equal to the derivative of L with respect to phi. In other words, the square bracket has to vanish for all points in space-time. And this is called Lagrange's equation. So this is this quantity unpacked. And that's the classical equation of motion for a Klein-Gordon field. We talked about that in the beginning of chapter 6. And in particular, if you have a single scalar field, the action density looks like this, or in more elaborate notation, it looks like that. Anyway, Lagrange's equations then are like this. In other words, their second derivatives of the field is equal to m squared times the field. And this is the Klein-Gordon equation. I should have said the beginning of chapter 7, not beginning of chapter 6. If you have several fields, you have several Lagrange equations, and it looks like this. So K is just an index of which field it is. It looks like that. Now, one of the things that people have made have been interested in a lot for the last 100 years or so is the connection between symmetries and conserved quantities. And the first, either the first person or one of the first people to figure this out was a woman named Emmy Noether, who was teaching at Bryn Mawr, I think. Anyway, suppose we have a transformation of the coordinates or the fields and their derivatives that leaves the action density invariant. Not the action, but the action density itself. We call this a symmetry of the theory, and it implies that something's conserved. So what we're saying here is that the change in the action density or the change in Lagrangian is 0 when you change the fields. And we're imagining we have several fields here because it often turns out that this happens, these symmetries occur when you have several fields. But also when you have one field, we'll we'll see about that. So you have several fields. This is the change in each field. And there's also the change in the derivative of each field. And so that's the derivative of the change in each field. And that's 0. And now we replace this by Lagrange, use Lagrange's equation to replace this derivative with this thing that's inside these brackets here. And we just keep this term. And now we notice that this term plus that term are the total derivative. It's a derivative of this sum. And the sum is the change in the field times this derivative here. Let me just, if I can, put a little more space here. Just want to move that delta phi out just a tad. Anyway, what this is saying then is that this thing here is conserved. And let me also put another space here. Okay, so this says that this current is conserved because it has a 0 divergence. That is, and what does this mean? D0, dA, JA. So that 0 equals, so that's 0 equals the time derivative of J0 plus the divergence of the 3-vector part of J, where J is this. And in particular, that means then that there's something that's conserved, and that's an integral over the volume of J0 d cubed x. Now, I should be a little careful here. I don't mean that J0 is necessarily conserved inside the volume. What I mean is the time value, the time derivative of the integral of J0 throughout the volume, which is the integral of the derivative of J0 throughout the volume, that this, because of this equation here, in other words, this equation tells us that D0, J0 is minus the divergence of the current density, and K going from 1 to 3 here. Yeah, I should have written that in vector notation. And so that is the current density dotted into the area. So maybe I'll rewrite that 7, 4, 7, 3. So in other words, what this is saying is that QV dot is equal to minus the current density dotted into the area of the volume. So basically the amount of stuff inside is increasing according to how much stuff is coming in through the surface, or it's going down because of how much stuff is leaking out through the surface. And if the surface is at infinity and nothing is happening at infinity, then the total amount of charge Q is conserved. So the integral over all space is conserved. Now this thing that's partial of L partial phi I dot, this is called the momentum conjugate to the field phi I. And so it's the sum of the momentum, the momenta dotted into the change in the field, if the change in the field leaves the Lagrangian invariant. And that sum then is the charge density. And as an example is an ON symmetry. So suppose you have n different fields, all of them scalar fields, and they all have the same mass. So then there's a lot of symmetry here. This is just sort of an n vector dotted into an n vector. And suppose A Now I'm a little puzzled. And A, right. Suppose A is a constant antisymmetric matrix. Then if you change the fields like this, the change in the ith field is some small number times Aij phi j. So what's the change in the Lagrangian? Well, it's going to be an Aij phi j in the m squared part, and then an Aij for all these guys. I don't know why I wrote this thing backwards. So let me write 477. But now the phi I and the phi j, that product is symmetric. Aij is antisymmetric, so this is 0. dA phi j and dA phi I, that's symmetric. So this, and Aij is antisymmetric, so that's 0. The charge then is the pi i's times the change in the phi i's, and the change in the phi I is Aij phi j. And so what do we have here? We have n minus 1 over 2 antisymmetric n by n imaginary matrices. They generate the group On of n by n orthogonal matrices. A simpler example, in fact, I probably should have done this one first, but anyway, is conservation of angular momentum. And here, what we imagine is an infinitesimal rotation by about the axis theta. And the magnitude of the rotation is the length of the vector theta. And so the change is theta crossed into x. This is the, your vector product. And so the change in the scalar field is the gradient times delta x. Delta x is theta cross x. And then, you can shift these things around because this is all, this thing there is actually a sum epsilon ijk di phi, only one phi, so let me get rid of that last thing. Di phi theta j xk, and you can then just sort of cyclically permute that so that you have epsilon j ki di phi theta j xk, and so that you can say is theta dot x cross gradient of phi. And that's what I've written here. If the field changes because it has spin, then you have an extra term. But if you forget about that, you just have the pi's times the change in the fields. And this is a formula for the angular momentum of the field, and this of the fields, and this is, or of the, if it's a single field, then this is the angular momentum of the field. If you have several fields, and I added spin, I probably shouldn't have done that, but anyway, then your angular momentum that's conserved is the integral of this thing, where you sum over all the fields as well as the spin things. All right, I'll come back here on Tuesday, and I'll try to finish this chapter on Tuesday, and then we can go on to the next chapters, and maybe even sneak in something from the second half of the book. In particular, I think these days people should know more about general relativity, so I'll see if I can sneak some of that in. So was there any, we have this chat box here. Does anybody want to say anything here? If not, I'll just say goodbye. I hope everybody's vaccinated, and look both ways crossing streets. And I guess I'll see you Tuesday. So I don't see anything happening in the chat. So I'm going to then stop and say, have a nice weekend.